Madam, screen share பண்ணிட்டு விடுங்க. Madam, screen share பண்ணிட்டு விடுங்க. Sir, you can share your screen.
Is already sharing there, sir?
Right, now it came.
Okay.
So now it is in live stream. Huh?
Okay, sir.
Okay. Now 11 o'clock. Shall we start the program?
Yeah, we can start.
Right. Okay, good morning. Myself, Professor D. Karthikeyan, Principal, SNS College of Pharmacy and Health Sciences, Coimbatore, and convener for this session. Sir, on behalf of management, faculties, and
Is already sharing there, sir?
I welcome all the participants to this two-day
So
now it is in live stream. And
Okay,
this
okay.
webinar will have first introduction. 11 o'clock. Shall we start the program? Then presentation.
Yeah, we can start.
And response to the
Okay,
good morning. And finally, vote of thanks by the Principal of College of Pharmacy and Health Sciences, Health Sciences, and convener for this session. Any participants have any faculties, queries?
Is already sharing there, sir?
I welcome all the participants to this two-day. Today is the first day, and today's speaker is Dr. Thiyagarajan. And this webinar will have first research associate, Helmholtz Institute of Pharmaceutical Research, Saarland University, and finally, Saarland University of Saarland, Germany. And he is going to talk about teach to reach the land. Production and quality control of dry powder. Tomorrow we are going to have the second module. Dr. Shiva Prasad Reddy, State Authorized Chief Administrative Pharmacist. He is going to talk about the pharmaceutical practice and pharmacist service in Denmark. He is going to talk. Let me introduce the today's speaker, Dr. Thiyagarajan. Production and quality control of dry powder. Tomorrow we are going to have the second module. Dr. Shiva Prasad Reddy, State Authorized Chief Administrative Pharmacist. He is going to talk about the pharmaceutical practice and pharmacist service in Denmark. He is going to talk. Let me introduce the today's speaker, Dr. Thiyagarajan. Production and quality control of dry powder. Tomorrow we are going to have the second module. Dr. Shiva Prasad Reddy, State Authorized Chief Administrative Pharmacist. He is going to talk about the pharmaceutical practice and pharmacist service in Denmark. He is going to talk. Let me introduce the today's speaker, Dr. Thiyagarajan. Production and quality control of dry powder. Tomorrow we are going to have the second. Is the first day. Dr. Shiva Prasad Reddy, State Authorized Chief Administrative Pharmacist. He is going to talk about the pharmaceutical practice and pharmacist service in Denmark. He is going to talk. Let me introduce the today's speaker, Dr. Thiyagarajan. Production and quality control of dry powder. Tomorrow we are going to have the second. Is the first day. Dr. Shiva Prasad Reddy, State Authorized Chief Administrative Pharmacist. He is going to talk about the pharmaceutical practice and pharmacist service in Denmark. He is going to talk. Let me introduce the today's speaker, Dr. Thiyagarajan. Production and quality control of dry powder. Tomorrow we are going to have the second. Is the first day. Dr. Shiva Prasad Reddy, State Authorized Chief Administrative Pharmacist. He is going to talk about the pharmaceutical practice and pharmacist service in Denmark. He is going to talk. Let me introduce the today's speaker, Dr. Thiyagarajan. Production and quality control of dry powder. Tomorrow we are going to have the second. Is the first day. Dr. Shiva Prasad Reddy, State Authorized Chief Administrative Pharmacist. He is going to talk about the pharmaceutical practice. 2009. Yes, today we have such a wonderful personality, Dr. Thiyagarajan Durairaj with us. And
the lobes and small branches are considered to be branchioles, and this microstructures and are branches containing alveolus and respiratory branchioles Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. Those are microstructures and small branches containing alveolus, bronchioles and respiratory bronchioles. So, what advantage this tripolar engineers gives us? Tripoders are more stable and provide us the freedom to load biomacromolecules, because in case of meter dose inhalers, if you put the biomacromolecules and as well as the propellant, there will be coagulation or disintegration of the biomolecules will happen. So this can be overcome by these tripolar inhalers. Then now let us see how do we produce these tripolar formulations. So these tripolar formulations can be produced as a whole active ingredient can be taken without adding any excipients. We can just produce this whole active ingredients as a microparticles, or we can make this active ingredients into nano suspension and put it in the excipients like a sugar-based excipients like lactose, fructose as well as trehalose. Then make the microparticles and the nano suspension will be embedded in them, or we can make a slightly bigger solid nanoparticles of the drug and we can put it in this sugar, then make the microparticles. Then we can have a system with nanoparticle in microparticles. Also we can make this nanoparticle, we can load this drug in the sophisticated soft materials like liposomes and like functionalized liposomes. Then load these liposomes in the microparticles so that it's like a well organized microstructure which can deliver active materials through liposomes. So we have to consider that we have to take the excipients which would be easily dissolvable as well as degradable. So some examples are lactose, fructose, trehalose, as well as some other sugar. In some cases, people also use a complicated sugar to make the particles like slightly heavy so that it can be uptaken by the macrophages quite easily. And leucine generally used to protect the surface and keep the particles well dispersed. And also temperature for the spray drying should be lower than 100 degrees Celsius for biomolecules and soft materials, because in case of higher temperature these biomolecules can degrade as well as the soft materials can degrade its nature. And all materials should be non-toxic and non-allergic, because this has to be administered through the nasal route as well as from the mouth. So people should not get the cough to expel this drug while inhaling. So I have in my career I have seen these two spray dryer, like Bookie 90 nano spray dryer as well as Bookie 290 spray dryer, which is available with us in the same institute. And I also got the information from Procep T spray dryer chiller, which is quite big in case of size and can produce much higher volume. But the advantage with the Bookie spray 90 nano spray dryer is it can take the smaller volume, like minimally like 5 ml of the medications can be spray dried, and it can produce very defined microstructure with that material. In case of Bookie 290, we have to take minimum of around 20 to 30 ml. So for research purpose, it is like a huge volume. So to start with. So I'm going to talk about Bookie 90 nano spray dryer, which I am very convenient and also which I am very comfortable with it. So Bookie spray dryer, the basic structure is the heater is on the top, and we have a spray dryer, and the spray dryer will disperse like droplets, and these droplets, when it's traveling through this distance, it can get dried and it will become microparticles, and these microparticles will be collected based on the surface charge on this electrode, and this electrode is like this circle metal frame, and we have to scrap the microparticle from this circle metal frame. And I will also show that just how the modern recent spray head will be. The recent spray head has a chip with them, which is a nebulizer, and which can be cleaned quite easily, and also like it's very convenient to open. And this whole setup will come around 4 to 5 feet, and the other version also has slightly taller, like you can have a two frames higher, and it will be around 6 feet, and which is available in our lab. And I just wanted to show some of the videos, like how the spraying works, like in operation, like where here they have shown like three different like spray head is used, and they have shown how it is been like that is dispersed. So while production you may not see the difference, but you will see the difference in the particle size later. And I also would like to show some of the example microparticle which I produced in the lab. So in the first case, I have used only the lactose leucine solution, and the particles are made which is around 2 to 5 microns, and here slightly bigger particles are there. And then I introduced nano suspension into this particle. The particle size got slightly reduced, but the particle properties slightly were maintained the same. But I also introduced the nanoparticles of some like anti-TB drug to the lactose leucine solution. Then the particle shape has totally changed, but the size ranges will be almost same. So the next I just wanted to explain how do we do this quality control in the lab scale. We have a conventional analysis like to study in any pharmaceutical product, like angle of repose, where we can see the flow property of the powders, and powder density analysis, where we can check how, like by tapping method, size measurements by static light scattering, and powder X-ray diffraction, where we can study whether the particles are amorphous or crystalline, and also we can do FTIR to check the particles nature, and the basic drug load can be calculated using UV or fluorescent or some other HPLC method. In a modern analytical technique, some of the other things also can be considered like for the after the production, which are like aerodynamic properties by next generation impactor and stability of active ingredients by biological assays. Like if I take some antibiotic or some DNA or RNA, I have to like make sure that it is still active after the production. Then we can also check the stability of DNA by gel electrophoresis, like where we can see the intact DNA by running gel electrophoresis and protein expression analysis for genetic materials. So if I'm sending some mRNA or siRNA, then we have to see the expression in the living cells by seeing maybe the color change or Western blot or some other method. And also gene expression studies in case of anti-cancer therapeutics, because most of the cancer are coming for like by in the damage of genetic materials, and also like ELISA or Western blotting for protein therapeutics as well as some vaccine candidates. So in a conventional method, how do they do angle of repose? They will take the funnel type in a normal like lab. They will actually take the funnel and they put the powders, and you may need 50 to 100 grams of powder, and they will make the repose. Then they'll calculate the angle. This angle considered to be angle of repose. There are some specific equations to calculate this angle of repose, which tells how the powders flow. So if the powder is like sticking to each other, the angle will increase and it will be a like taller repose. And if the powder is flowing very nicely or it has a very good flow property, the repose height will reduce. So thus the angle also will reduce. So then further, this powders also can be studied via X-ray diffraction patterns, and this X-ray diffraction is a technique to study crystallinity of the powders. So in crystalline materials, the molecules are arranged in a particular fashion so that when you apply the light to the powders, it can diffract in a particular fashion in any concentration. So this can be this is like this is a what is it? This is a quality measurement for the crystalline powders. So if you produce some powders amorphous, this will not have this steep peak. This will have the broader peak, and also if you have the crystalline drug, which will have the sharper peaks. So based on that, you can differentiate what kind of powder you are producing. As well as here also we have to consider that in case if you want to dissolve the powders very quickly in the mucus and penetrate to the deeper lung, you should have the amorphous powder. And if you want some depot kind of therapy, like if you keep the powders in the lung and it may settle down in the mucus or on the top of the cell line, and it can stay there for longer time and release the drug slowly by slow disintegration. So for this, you need to maintain the crystalline structure in the formulation. Then further, these formulations can be analyzed using static light scattering. In static light scattering, it is a similar similar method like dynamic light scattering, but here the particle size is quite big. Thus, the static light scattering is used, and the scattered light will be measured in the particular angle to measure the average size of the particles. So here the scheme shows that how this works in the machine, the Partitia from Horiba, which is generally used to measure the size in pharmaceutical industry. And here the light will be passed through this bigger pivot, which may take the volume of around 15 to 20 ml, or in some bigger pivot it may take around 100 ml. So there the powders will be dispersed and sprayed through this mechanical device. Then the light will be passed through this pivot, and based on the scattering pattern, we will calculate the particle size. So in my case, I also personally checked this one with my formulation, and we could see the size ranged from 1 to 10 micron different this one, and the average size were like 2.9 micrometer, which is perfect to administer in the human lung. Then I would also like to show some aerodynamic properties, how it is being done, why we have to consider this. So if you see like typically if you take any particle from 10 to 30 micron size, it can deposit at the nose as well as like some pre throat regions, and the size smaller than that, around 2 to 16 micron particles, can go through trachea, bronchi, bronchioles, and terminal bronchioles, and these are called conducting zone. Then respiratory zone, only the particles around like 0.5 mm to like like smaller than 2 micron particles can reach. So which is also like and also like I just wish to show this video. Just a minute. Yeah. So here you would see like how this size can be separated using the devices impactors uh, from the industry. Here you could see like the arrangement of various plates of different size to segregate the powders. Yeah, so that was like quite a big video, so maybe like next time I can explain better. So here also the same principle, I can explain it better. So the next generation impactor is a device like mechanically behaves as a lung, which can separate particles based on the aerodynamic size. So if you see here, the particles will be sent through this nozzle, and we have 8 different stages. Each stages can segregate particle size of different size, 8 to 0.3 micrometer, and initially the powder will be kept on the capsules, and this capsule will be given to the tripowder inhaler device, and this will be broken and supplied, and this after that this sample will be supplied in the normal breathing like speed, which can call around 60 liters per minute, and these powders will deposit based on the size in different stages, and these stages can be collected, and can be powder can be scrapped as well as can be collected with any other liquid, and this will be analyzed later like how much each size of the powders are deposited. So typically size 4.46 micron to size 0.94 microns are considered to be suitable for deeper lung applications, which is also called respirable fraction. In certain cases, we could see that this one example which is we have done in our lab. I'm showing here the detail. So here we have taken the 4 different powders which is produced in our lab, and we could see the larger aggregates, they are settled down in tube, which is like this this place, and the stage 1 didn't collect much powder, which is also like favorable because the stage 1 is not considered to be a deeper lung, and from stage 2 to stage 5 we could see like a larger portion of the powders were collected, which are like around 60 to 70% of the total population, and stage 6 to stage 8 considered to be like it came around 10 to 20% this kind of wastage, or it can go or land, which we don't know in the real application. But generally a formulation which can give around 60 to 70% of this respiratory portion considered to be a best formulation to be administered. So with this I would like to end the talk, and I would like to acknowledge like and also like I didn't want to like go further about the further analysis because those are a bit complicated for the beginners, like for the bachelor students to understand. So uh, so those things like we can understand later, but basically what we have to do is like initially the conventional analysis like XRD, FTIR, this analysis we have to do. Later, typically the aerodynamics diameter is very important to study. These two aspects if you study, then for the biological assays, if you do it through the cells, that is more than sufficient for the initial sample screening. And later, if you're going for the real clinical study, you have to do all the like in-depth analysis, like genetic material expressions, everything. So with this, I would like to acknowledge my professor, class Michelle Lair, and my colleague Brigitta and others. And as well as I would like to thank Professor D. Karthikeyan, Professor Kumar Nalasimham, Professor Dr. Nalin Himal Kumar, Dr. Subramanian, Dr. Rajalakshmi, and also Lalit for giving me this opportunity to present some aspects of this dry powder formulations with you and share the experience with you. And also, I'd like to invite you all for our next workshop and also conference, which is happening next year. This is also postponed due to Corona this year, and this is happening next year, September 2021. So, we will be happy to host you if you would like to attend the conference. Thank you all. Hello?
Thank you very much. Yeah, thank you very much, sir.
Yes, sir. Any questions?
Now the session is open for discussion. Dear participants, any queries, please send chat messages. Please check it, sir. Anything is there?
Yeah, already I could see. So you have asked some question about any instruments to measure the angle of repose.
Yeah, please respond.
So the thing is, in my lab, when I was doing my B pharmacy, what we used to do is like we used to take the graph sheet or a sheet, and we use the funnel, and we used to like use the powder. Then like based on the circle diameter and as well as the height, we will calculate the angle of repose directly. That is a very conventional.
That is the traditional method. Yeah.
Traditional method.
Yeah, conventional.
So more.
Method we are,
yeah. So there you have to waste lot of powders, but in the modern, I'm not very like sure about the modern instrument name, but there are instruments available to measure this in a very small volume.
Any other questions?
Could I also stop the screen share?
Yeah, let it be. No issue.
Okay.
I think there is no further questions. Now I request Mr. Anand Babu to present the vote of thanks. Mr. Anand Babu.
Yes, sir. Good morning to everyone.
Yeah.
On behalf of SNS College of Pharmacy and Health Sciences, I take this opportunity to propose the vote of thanks to our speaker, Dr. Thiyagarajan, research associate from Helmholtz Institute of Pharmaceutical Research, for given the knowledge of production and quality control of dry powder. Thank you, sir.
Thank you.
And I would like to thank our beloved principal for his enthusiastic support. We organizing team are thankful to our management for their support to conduct this international webinar. And also our heartful thanks to the faculties and students from various organizations and our own institute. And finally, I would like to thank over the technical team supported for this international webinar. With the warm words, a kind message, we move to the end of today's webinar. Thank you, sir.
Thank you very much. And I take this opportunity to thank particularly Mr. Lalit Mukesh. He is the person behind the screen to arrange this webinar. Thank you, Mr. Lalit Mukesh. And thank you very much, sir.
Yes, sir.
Thank you.
Thank you, sir. Thank you very much for the opportunity. Thank you.
Thank you.